It has to go based upon the constant units. And so this has to be in atmospheres, this has to be in liters, N is in moles, and T is, of course, in Kelvin, which is what it had to be in the previous relationships as well. Now, that constant, 0.082, sometimes there's a 1 on there, it's got several different levels of significant figures. That constant would be given to you. So you don't have to memorize that constant. It will be something that will be made available to you. So think about this. This is a mathematical expression in 4 variables. If the constant value is given to you, then that's not a problem. But the other 4 are variables: pressure, volume, moles, temperature. Give me any 3 of those variables and I can get the 4th variable simply by solving for it. And so that's typically what we do with ideal gas law problems. Now, one of the things that is a worthwhile thing for us is to determine what the volume is for 1 mole of gas at the conditions of STP. Do you remember what STP stood for? Standard temperature and pressure, and what were the parameters? What were the conditions? 0 degrees Celsius and 1 atmosphere. And so let's calculate what's called the molar volume. Let's find out what the volume would be for 1 mole of any gas. Remember, the ideal gas law stands for any gas. Now, it doesn't have to be a specific gas. Any gas at STP. And so what we're saying is N is equal to 1 mole, P is equal to 1 atmosphere, T is equal to 0 degrees centigrade, which is 273 Kelvin, and R is 0.0821 liter atmospheres mole Kelvin. So, can I solve my ideal gas law for volume? Sure. Volume is simply equal to nRT over P. So if I plug in all these numbers, 1 mole, 0.0821 liter atmosphere mole Kelvin, 273 Kelvin over 1 atmosphere, then if you just look at the units, and remember we always encourage you to use units, the moles cancel here, the K's cancel, atmospheres cancel, and I'm left with a liter value. And that volume turns out to be 22.4 liters. And essentially it's a per mole, because we did it for 1 mole of the substance. So 22.4 is called the molar volume. It's the volume that 1 mole of a gas would occupy at STP. Now, of course, if we changed any of those conditions, change the temperature, change the pressure, then the volume would be different. But we could still calculate it. We would just be changing one of the parameters over here. But since STP is a common set of conditions, we now have the value for the volume that would exist for any gas at those conditions. Now, one of the things we look for when we come up with a relationship like this is, are there some practical applications of this relationship? And the answer is yes, there are some great practical applications of this relationship. And so let's take a look at one of those by a problem. Let's consider a substance called benzene. Empirical formula is CH. Now think back to a couple of years ago when we started this class. We did empirical formulas. we found that if we were given certain percentages of elements and so forth, we could calculate an empirical formula. Good thing to go back and look at sometime because what? In a little over a month, we're going to be looking at a final exam, and that final exam is going to cover everything, and so empirical formulas are going to be fair game. Once we got the empirical formula, the next step we said was to try to go to a molecular formula. In order to do that, we needed an additional piece of information. Do you remember what that additional piece of information was?
Molar mass.
It was the molar mass, the molecular weight or molecular mass of the substance in order to make that definitive statement as to what the value was. And in those days, we just simply had to give it to you. Well, now we can see an experimental approach to finding that molar mass. So let's take a look at this problem. If I had .22 grams of the benzene and it occupies a volume of 3.5 liters at 27 degrees centigrade and a pressure of 289 torr, can I get the molecular mass, which in turn would allow me to get the molecular formula of this compound. So on the final exam, it might be a question, imagine this question, that gave you the percentage of carbon and hydrogen, then gave you this information and said, get the molecular formula. So you'd use the percent information to calculate the empirical formula, then you would use the gas law information to calculate the molecular mass, and then combine those two concepts to get the overall molecular formula. So how would we do this? Well, I think when you're faced with a problem like this, the first thing you should always do is determine what am I asked to find. Now, in many cases, it's the question mark. Look for the question mark. If there's a question mark there, it's telling you to find this or calculate this or whatever. If there's no question mark, look for the command statement that says, do this, calculate such and such, find such and such. So we're asked to find the molecular mass. Then what do? Well, let's ask ourselves, what is a molecular mass? A molecular mass is defined as the mass per mole of a substance. So basically, the molecular mass is the mass, which we describe in terms of grams, per mole of the substance, which tells me what? This definition implies an arithmetic operation. This says to me that if I know some number of grams, and I know the corresponding number of moles to that number of grams, I can get the molecular mass. Do I know the number of grams of benzene in my problem? Yes. If I can find the number of moles that correspond to those grams, I've got the piece of information that I need. So how do I find that? Well, I realize they're giving me gas information here. And I have at my disposal always PV equals nRT. Be a good tattoo to get at some point. You're going to use this a lot. If you go on to chemistry 1212, this rides right along with you. We use it frequently in there as a relationship for some gaseous materials, finding out some parameter. And so what am I actually looking for in this equation, do you think? I'm looking for N. I want the number of moles that correspond to my 4.22 grams. So N should be equal to PV over RT. I go to my information, and the pressure is 289 torr. Can I enter that like it is? No, because why? Remember, that has to be in atmospheres. So I can do that conversion here, if you like, 289 torr, and there are 760 torr per atmosphere. So that calculation would give me the number of atmospheres that I have. Times the volume is 3.5 liters. Is there a conversion necessary there? No, that looks all right. So 3.5 liters over R, which never changes. For gas law relationships. And then finally T. So T is 27. Plus the 273, so what is that, 300 Kelvin. So if I run these numbers, I should get the number of moles of my gas, which is 0.054 moles. And so that tells me that the molecular mass must be 4.22 grams over 0.054 moles, or 78.1 grams per mole. Yes, ma'am.
Okay, so at the bottom of the equation, you have 0.081, that's approximately 0.082.
Yeah, you're right. That 2 is there, it's just hard to see. I'll make it a little bigger. Thanks.
And then 760 at the bottom of 289 came from there.
Ask that again.
Where is this?
What is it? 760. Remember that 760 torr equals 1 atmosphere? And so that's the conversion factor that I would use to change that torr value into atmospheres. Okay, now what do? Well, remember, back in the empirical formula days, we found an empirical formula weight. What would be the weight of this empirical formula? Carbon is 12, hydrogen 1, so the empirical formula weight is 13. And then we took the molecular weight and divided it by the empirical formula weight and hoped to get a whole number, an integer. And then we said, what? Take that integer and multiply everything in the empirical formula by that factor. So our molecular formula should be C6H6 in this particular problem. Questions? Another important application for us is a link to stoichiometry. If I'm given a certain amount of gas in terms of pressure or a volume, and I have the other parameters, and I can solve for moles. Remember, stoichiometry always deals with moles of substances and how they react together, so I can convert to moles and come up with that stoichiometric relationship in some problem. Okay, so let's expand upon this a little bit and ask the question, what if we had a mixture of gases? Suppose I had 2 or more gases present in a sample. Can I work with those pressures and volumes and so forth? So let's go back to the ideal gas law. PV equals nRT. And I want to rearrange this just a little bit. I'm going to first of all divide both sides by V. So I get that the pressure is equal to nRT over V. or the pressure is equal to N. Let me group it like this. Doesn't really change anything, just another way of looking at it. If I have a system of a mixture of gases, several different gases, then the pressure for that system is going to be equal to the total number of moles of gases times RT over V. Now RT over V will probably be a constant, because what I'm going to do is I'm going to hold the temperature constant, I'm going to hold the volume constant for my sample. These things are all in one container and so forth. And so I have this mixture taking place here. So what we concluded was that the total pressure is equal to the total number of moles times RT over V. Now, the total number of moles would be what? Well, I would simply take all the gases that I was given and I would add their moles together. So let's say it's the moles of gas 1 plus the moles of gas 2 plus the moles of gas 3, and for however many gases I have in this mixture. You can have 2 or more if it's a mixture, so I have them all laid out here. And then this is still times RT over V. So what I want to do with this expression is to expand it. I want to take this term right here and multiply it by everything that's in the parentheses. So I would get that the total pressure would be equal to N1 times RT over V plus N2 times RT over V plus N3 times RT over V plus however many other terms there happen to be in that expression.
Question.
Yeah.
You can't just add up all the N1, 2, and 3's together and then multiply by RT over V.
Sure, that's what the top expression is saying. Okay? The reason I'm doing this is to show you a new relationship that we're going to have. So if I separate them out, then understand what this is. This is the pressure of gas 1 alone. So that the total pressure becomes the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. So what we're saying is that the total pressure is equal to the sum of the individual pressures, which we call partial pressures. And so this is actually known as Dalton's law. Dalton's law says that the total pressure is the sum of all the partial pressures of the gases present in the mixture. And this becomes very useful for certain applications. For example, in the laboratory, if we are going to collect a gas into a bottle, the way we do this is to fill the bottle with water and then invert it into a dish of water. So this is filled with water. And then we take a rubber tube and put the gas in here. As the gas comes in and bubbles upward, it displaces the water. It forces the water out the bottom of the bottle. And so the gas will start to collect in the top of the bottle. And after a while, I've got a situation that looks like this. After a longer time, it's going to look like this. After a longer time, I'm going to have a completely filled bottle of the gas that I want to play with. Okay? And so let's say I've collected hydrogen gas. The difficulty in this maneuver is that that's not the only gas present in that bottle. I totally filled it with water. I put only hydrogen gas in there. What other gas could possibly be present? No. There's no oxygen. I've taken all the air out by putting water in there first. Is there another gas in there? It's water vapor. So the other gas that's in here is water vapor, which I really can't eliminate because I'm collecting this over water. The water is going to vaporize to a certain extent. The good news is that the water vapor usually depends only upon temperature. And so I have a book, a handbook of chemistry and physics, for example, which you can find in the library, or you can probably find this number online. You can actually find out what the partial pressure is for water at a particular temperature. And so can I determine what the pressure of the hydrogen gas is? If I know the total pressure here, and I say, okay, it's at 25 degrees centigrade, I would go to the handbook and I would look up what is the water vapor pressure at 25 degrees centigrade. Then to get the hydrogen pressure, I could subtract it from the total and come up with just the hydrogen pressure. We have our students do this in the kitty chemistry laboratory, chemistry 1151. We have them do an experiment where they collect hydrogen gas by a chemical reaction with an acid and a piece of magnesium, and that hydrogen gas is collected in a tube. And we use the experiment to measure what's called the atmospheric pressure, the pressure that is out here. And the total pressure that they measure is determined by setting the liquid levels even at some point where they take the volume measurement and they determine what the volume of the gas happens to be. But that's for the total pressure, the total atmospheric pressure. And then they calculate the amount of pressure that comes only from the hydrogen, and then they have to add in the amount that comes from the water that's there. And so there's a way to calculate this from using the ideal gas law and knowing how much magnesium, how much acid they use, and so forth. They can determine how much hydrogen is present, get the pressure of the hydrogen, but then they have to add in the pressure of the water to get the total atmospheric pressure. So all of this is outlined in their experiment. I don't think 1211 does a gaseous experiment like that. You're going to be doing 2 gaseous experiments toward the end of the semester. One of those is Charles' law. You're going to place a sample of gas into a variety of different temperature containers to measure its volume. And then you're going to do something called Graham's law, which has to do, coming up for us, the diffusion of gases through space. Gases move based upon their molecular mass. All right, questions here? Well, if we look at one of these gases in our mixture, let's take this one, gas number 1. We know that the pressure for gas number 1 is equal to the moles of number 1 times RT over V. We also know that the total pressure is equal to the total number of moles times RT over V. So what would I get if I took the pressure of gas number 1 and divided it by the total pressure of this sample? Well, let's just make the substitution. This would be equal to N1 times RT over V, and this would be equal to N total times RT over V. But at constant volume, constant temperature, and R, known as the gas constant, all these values are constant, so the R's and the T's cancel, the V's cancel, and so I'm left with the moles of gas 1 over the total number of moles. And this is known as mole fraction. This ratio right here is known as the mole fraction. And it's simply the number of moles over the total number of moles. Well, let's rearrange this a little bit and look what we get. That the partial pressure of our gas number 1 is equal to, mole fraction is usually symbolized by the Greek letter chi. So we'll call it chi1. This is equal to the mole fraction of 1 times the total pressure for that sample. So if we know the mole fraction, we can find the individual pressures of our substances. Now, the mathematics stuff that we've derived here and have developed here from experimental evidence is great for describing the physical systems and predicting their behavior. But often we would like to add a physical model that helps us to understand what's happening in terms of these gaseous particles. And so we could ask the question, we know that when a gas is heated it expands, but why is that the case? Why should it expand? What's physically occurring? And so back in the 1800s, the late 1800s, they developed a model called the kinetic molecular theory of gases. And the kinetic molecular theory of gases is a set of statements that helps us to understand what is taking place in terms of these gas laws. And so the first statement in the kinetic molecular theory is that gases consist of a large number of particles, and these particles can be molecules or atoms, and that they are in continuous and random motion with respect to each other. So basically the picture we're drawing is that if you have a container that has a gas, then the gas consists of this large number of individual particles. Now remember, based upon the work of Avogadro and Gay-Lussac, we don't care what that gas is. We don't care if it's a molecule or if it's an atom, if it's a big molecule or a small molecule or a medium-sized atom. We don't care. It's the number of particles that's important. And it's those particles that we can represent with a dot. And so what are those particles doing in this sample? They're moving. How can we prove that? Suppose I wanted to prove to you that the particles of a gas are in motion. Is there something I could do in this classroom that would maybe convince you that that has to be the case?
You could spray a certain scent.
I could spray a certain scent, perfume, for example. And if I did that, would you detect it eventually somewhere in this room? The only way you can do that is if those particles that make up that scent, that perfume, were traveling through the air and made it to your personal perfume detector, okay, your nose. And so the gaseous particles have to be in motion. And so we know inside the sample that they're not just standing there looking around talking to each other. They are in constant motion with respect to one another. And it's random motion. Now, random in the sense that if there's no interaction, and this particle is moving in this direction, he's going to continue to move in that direction. He doesn't have a choice but to move in the direction in which he's propelled. But if he collides with something else, then his direction can change. And so that's why we call it random motion, is because the motion is going to change based upon the interaction that takes place between the particles. The second assumption we make in the kinetic molecular theory is that the combined volume of all the molecules is negligible compared to the total volume of the container. In other words, what we say is that the gaseous particles are point particles. They don't have a volume associated with them. Now, in fact, that's a lie. That's not true. But the volume of the particle, water for example, is so small compared to the volume of the container that we can ignore the volume of the individual particle. So we consider these to be a point. Now, go back to mathematics. What's the volume of a point on a number line? It's infinitesimally small, and so it has no volume associated with it. And that's the assumption we make for our gases in the kinetic molecular theory. Now, this explains the low density of gases. If you look at the numbers, the densities of gases are very low compared to, say, a density of a liquid or a solid. And it also explains the compressibility. Can I push these particles together? Well, if the particles are point particles and have virtually no volume, and they exist in this huge volume container, there's a lot of space between the individual particles. And that means if I exert some pressure, some force, and push them together, I can do that. that I should be able to get them closer to each other than they are originally. Now, can I do that with liquids? You don't know this perhaps yet, but in the next semester in Chemistry 1212, you'll have a chapter on liquids and solids. And one of the things you'll find there is that the liquid particles are relatively close together. They're right up next to each other. And so can I, with some force, compress them against each other? The answer is basically no. Liquids have very low or negligible or zero compressibility. In fact, our entire system of hydraulics depends upon that liquids do not get compressed in the process. And so when we pump liquids into a system, it causes a piston to expand, which drives a steam shovel or something like that. But gases, on the other hand, can be compressed. So they're very different from liquids or solids. The third point we make in the kinetic molecular theory is that attractive and repulsive forces between gas particles are negligible. In other words, we're saying that they ignore one another. Here are these particles, tiny point masses that have no volume, and they're moving rapidly inside this system, and they're pretty much ignoring each other. Now, occasionally they'll collide with one another, but when they collide with one another, we say that those collisions are perfectly elastic. They bounce off right off each other. And there's no interaction between them. So they're not attracted to one another. They don't repel one another.
Thank you.
The attractive and repulsive forces are negligible or zero. The fourth point is that collision idea, that the collisions are elastic. And what that means is no energy is lost when they collide together. Now in practice, pool balls on a pool table, you know that they'll collide together and they'll go off in different directions. And so that becomes a very good model for this kinetic molecular theory. If you look at pool balls on a table interacting with each other, going off in random directions when they collide and are hit with one another. But there's some energy loss in a pool ball. And so they eventually slow down. There's no energy loss in the collisions that take place inside of a gas. And so they continue to move at the same energy. Yes, sir?
What if they collide with another different gas, or solids or liquid?
If it collides with a different gas, there should be no difference. I mean, we're considering all gases to be these point masses, point particles, and so there's no interaction between particles. If it collides with a liquid, then what we're going to find in the next semester, okay, moving ahead to Chemistry 1212, Chapter 11, is that when it collides with the liquid, there can be a loss of energy. Now, I should say that here, there can be a loss of energy too. The energy overall is conserved. But think of pool balls on a pool table. If there's a ball sitting here at rest, what's its kinetic energy? Zero. And you hit the cue ball and it comes screaming across here, that cue ball has some kinetic energy. Now when it hits this ball right here, it can transfer that energy so that the cue ball remains stationary and the other ball goes off at that same speed. When we say the collisions are elastic, we mean that energy is not lost overall. But it could be lost for an individual particle. So this guy could go from a high kinetic energy to a zero kinetic energy by transferring all of its energy to the other particle. But if we look at the entire system, there's no loss of energy in the system.
Would that change the pressure?
No, should not change the pressure because on average, you have these particles moving at a relatively average speed, same kind of force being exerted. So statistically speaking, you have this mix that gives them one pressure. Okay. Now that is as long as I don't change the other parameters. If I don't change the volume, and if I don't change the temperature, then the pressure is going to stay the same. And that agrees with what we observed in the experimental field. We then, a fifth point in the kinetic molecular theory is that we talk about the average kinetic energy of the molecules. These molecules are all different in their energy, if we think about it. The chances of them all moving with exactly the same speed in this sample is astronomically small. You've got some that move very fast. You've got some that move very slow. Maybe some that are perfectly still at some instant in time and have zero kinetic energy at that point. But what we talk about is the average kinetic energy. So that guy that's standing still, it's not going to be very long before he's hit by somebody and starts to move again and now has a kinetic energy. And those kinetic energies are going to vary from one another, but if we total them all up and take an average, we'll find that there is an average value of the kinetic energy of these particles. And that average value of kinetic energy is, we find, is directly proportional to the absolute temperature. So once we fix the temperature, we have a fixed value for the energy of our gaseous system. Now, again, the average kinetic energy, or the kinetic energy of a particle, is given by 1/2 mv squared. So it depends upon the mass of the particle, and it depends upon the velocity of the particle, or the speed at which the particle is traveling. So a heavy gas is going to probably have a much slower rate of transport, a much slower speed than a lighter gas. Because what did we just say? One of the conditions of the kinetic molecular theory was that all gases at a particular temperature have the same average kinetic energy. That means if I have a sample of hydrogen and a sample of oxygen, both in the same size container, both at room temperature, both at 1 atmosphere of pressure, then those samples have to have the same average kinetic energy. But hydrogen weighs a lot less than oxygen does. So in order for it to have the same kinetic energy, what has to be true? Its speed has to be greater than the oxygen's. So just like real life, the fatter guys move more slowly than the thinner guys. So hydrogen, a relatively light particle, is going to move very rapidly, whereas oxygen, a heavier particle, is going to move more slowly. But each will have the same average kinetic energy, difference being in their masses. If the temperature of a gas rises, what do we think that does to the sample? Well, logically speaking, if we increase the temperature, are we passing energy into the system? If we pass energy into the system, what parameter there would have to change? Is the mass of the particle going to change?
No.
The mass is fixed. So in order to accommodate the higher energy, it means at a higher temperature there must be a higher velocity. Those particles must be moving faster. If those particles are moving faster, are they going to hit the wall a little bit harder? Hitting the wall is a measure of the pressure. And so what happens to the pressure as we increase the temperature of our gas?
It increases.
That pressure should go up. And we know that's the case. Remember, if we threw a paint can, an aerosol paint can, into a campfire, it'll sit there for a while and heat up, and then what? It'll explode because it's a sealed system, and you are increasing the pressure inside there to the point where the can no longer hold that pressure back, and it's going to explode. Another consequence of the kinetic molecular theory is that at absolute zero, all motion stops. So at absolute zero, the kinetic energy of the gas is zero, which is a little bit of a misnomer, because at absolute zero, we wouldn't have a gas. Everything condenses before that point. But ideally speaking, at that condition, at absolute zero, the particles are locked into position. They are literally frozen, so to speak. Now, a guy by the name of Graham was able to come up with a relationship for the effusion of a gas. The effusion of a gas is the movement of the gas through, say, a hole in a container, and how the gas might move out of that container through that hole. And as we just said, that probably is going to depend upon its mass, because the velocity depends upon the mass, and so what Graham found was that there is a relationship. He said that the rate under conditions 1 compared to the rate under conditions 2 for the gases would be equal to the square root of the molecular mass for particle 2 compared to the molecular mass of particle 1. I'm sorry? This is Graham's law, yes. Now you're going to validate this in the laboratory. What you're going to do is you're going to actually do this experiment here, where you have a glass tube that you clean out very thoroughly. And in one end, you're going to place a sample of ammonia gas. In the other end, you're going to place a sample of hydrogen chloride gas. Now, both of those are gases, and so both of them move. And when you put them at the ends of these tubes, if you do it simultaneously, they will move in opposite directions. So the ammonia is going to flow from here toward that direction. The HCl is going to flow from that direction towards this direction. The reason this is such a neat experiment is that these two guys, when they meet, they react with each other and they form ammonium chloride. But ammonium chloride is a solid. And so we can actually see the interaction between these two gaseous particles. So when you set this into motion, they start to drift down the tube like so. And at some point, you're going to see the development of a white ring that forms on the tube here where those two gases meet, because they form a solid white salt particle. Now, the distance that they travel will be different for each of these because these have different masses. The molecular mass of this guy is 17 grams per mole. This guy is 36.5 grams per mole. Okay? And we find that they should move according to this relationship. Now, here we talk about rates. Here we're talking about distances. And so the guy with the less mass is going to travel the greatest distance in the process. And so you're actually going to validate this relationship in the laboratory. We will try to do an example of this on Wednesday. I want to spend a minute here talking about the next exam. We're basically at the end of chapter 6. We've got a couple of things to finish up. I'm going to give you a sheet today. You can pick this up on your way out if you want. There's some gas problems to attempt. Might be fun. And so I think we need to look for an exam. So we can't have it Wednesday because